Welcome to Chemistry Insight. In my last video, I started discussion about the CSIR previous exam questions and its detailed solutions. And as part of the discussion, we have chosen a question related to rubredoxin. And also at the end of the video, I asked a couple of questions related to the spectroscopy and symmetry of rubredoxin. In this video, I'll discuss about the Mossbauer spectrum of rubredoxin. Well, Mossbauer spectroscopy in itself is a very big topic. It is not the part of our discussion, but I'll just restrict to the basics of Mossbauer spectroscopy. To witness a Mossbauer spectrum, the given chemical entity should have some unsymmetric electric field gradient. This unsymmetric electric field gradient, it could be generated from three different parameters. First one is it could be generated from unsymmetric electronic environment around the central metal atom or the ion, or it could generate from the unsymmetric geometry, or it could also generate from the unsymmetric ligand environment. So we have to check for one of these three parameters or the combination of these parameters. Well, in the case of rubredoxin, there are two different oxidation states. Iron could be present in +3, which is an oxidized state, or it could be present in +2, which is a reduced state. Let me begin with a high spin iron 3, which is an oxidized rubredoxin state. Electronic configuration is found to be E2 and T23 for a tetrahedral geometry, and both E2 as well as T2, E2 and T23, we can see that they are half filled. So as they are half filled, it is providing a symmetric electronic environment. So there should not be any distortion. The distortions induced due to unsymmetric electronic environment are not seen here. Or let us say in another way, we don't find any John-Taylor distortions. So John-Taylor distortions are absent, but there are some ligand-induced distortions because it is a biomolecule, and for most of these biomolecules, ligand-induced distortions will be under operation. And these distortions has a considerable magnitude. So therefore, though there is a pure tetrahedral geometry, which is one of the cubic geometries and do not possess any distortion, but rubredoxins are bound to possess some distortion to some magnitude, which is a ligand induced distortion. Therefore we expect a Mossbauer spectrum, but the magnitude is smaller, therefore there will be a small quadrupole split doublet. So this will provide a Mossbauer spectrum, the oxidized form. One peak will appear, and this one peak will give a quadrupole split doublet. We can see a peak around 0.7 to 0.8 mm per second. This is with respect to the oxidized rubredoxin. In case of reduced rubredoxin, it is a high spin iron 2 state with E3 and T23 configuration. Now once these electrons are filled up, we can see it is a E3 and T23 configuration. There is a unsymmetric electronic environment that is present. So there are also ligand induced distortions. Along with that, we also find some unsymmetric electronic environment. So we say that John-Taylor distortions are also under operation. So the ligand-induced distortion is coupled with the John-Taylor distortions, and the parameter of unsymmetry is increasing. So the overall distortion magnitude is relatively larger. So we can witness a Mossbauer peak with a larger quadrupole split doublet. So one peak will appear in the Mossbauer spectrum, but there will be a larger quadrupole split doublet. It is about 3.1 to 3.4 mm per second. So this is our discussion. Rubredoxin will provide two Mossbauer peaks, one for the oxidized state and one for the reduced state, and each peak will have a quadrupole split doublet. In the case of high spin iron 3, the oxidized state, the quadrupole split doublet magnitude will be less, whereas in the case of the high spin iron 2 reduced state, the quadrupole split doublet will have a larger magnitude. Thank you.